Hi, so in this paper we are improving the latency of network update schedules in software-defined networks using a novel Petri nets based approach, and this is joint work with Glavind, Niels Christensen, and Jiri, Srba. So the motivation for this work are two trends in networking. On the one hand, networks become more flexible and adaptable, enabled by software-defined networking, virtualization, reconfigurable optical technologies. And this introduces a vision of more adaptable and dynamic networks that are like self-improving and run more efficiently and at a better performance than static networks. And at the same time, networks become a critical infrastructure of the digital society. So there are increasingly stringent dependability requirements. And in principle, this could be a trade-off. So improving performance, making it more dynamic, and at the same time, making it more reliable. And in this work, we are mainly considering the problem of a network operator that need to ensure critical properties in the network, like reachability. Traffic can always reach from A to B, loop freedom, so there's no loops in the routing, policy enforcement, that traffic is not going through certain places in the network, or traffic between A and B always traverses a certain waypoint or a sequence of waypoints. And this is challenging already in classic static networks, but it's of course even more challenging in dynamic networks that self-adjust. Specifically, we are considering the problem of providing efficiency and reliability in the context of dynamic routing. So how to quickly change from an old route to a new route in a consistent way. And that's this problem is known as the consistent network update problem, and the motivation for such route changes are manifold. It can be dynamic traffic engineering related, changes in the demand, changes in the security policy, service relocation, maintenance work, etc. And specifically, we focus on software-defined networks. So that's a programmable network that's managed by a controller. The area here is fairly active. So a recent survey discusses more than 100 related papers. And it's become especially active in the context of software-defined networking. I also refer to the keynote by Nate Foster at Connext 2018. And we actually specifically will compare ourselves to the NetSynth paper. So this is this paper by Nate Foster that we are trying to improve with our approach. Good, let's consider some background. So the challenge in this context is that if a SDM controller wants to change from an old route, here the black route, to a new route, here indicated in blue, this communication channel between the controller and the network is asynchronous, and updates at the different routers or switches may happen at different times. So for example, if this update happens first, then temporarily, the forwarding will look like this, like indicated in red, that traffic will flow as follows. And that's problematic because now the waypoint is violated. So the waypoint property is violated. So traffic is bypassing the waypoint. Another example, if this update happens first, then temporarily traffic will go in a loop. So the challenge here is to update the network in a way that even during the update, these properties are maintained. And the popular approach to ensure such transiently consistent network updates is to proceed in multiple rounds. So the controller sends out a set of updates to a subset of the switches and then waits for acknowledgements and then updates the next set of switches. And if you schedule these updates in a good way, you can maintain some of these properties, the desired properties. So the motivation for our paper is that current approaches are either fairly pessimistic in that they assume arbitrary delays at the switches when you update them, and this can make the update schedule unnecessarily slow. Other works are assuming a fairly optimistic model where updates can be timed precisely and synchronously, but this actually requires special hardware. So in our work, we want to leverage the timing information that is there to speed up and synthesize faster network update schedules. So we present a fully automated approach to optimize the performance of network update schedules. And specifically, we synthesize the waiting times between updates, accounting for the characteristics. So we have packets of different types and different types of switches, and we can account this for these different types to improve the performance. And our approach supports a wide range of consistency properties, including waypoint enforcements or sequence of waypoint enforcements, loop freedom, blacklist enforcement, black hole freedom, etc. So our approach is to rely on formal methods and specifically on a novel type of Petri nets. So Petri nets are a powerful modeling language for distributed systems in general, describing configurations based on tokens that are located at places. And in our approach to synthesize these improved network update schedules, we introduce an extension where tokens also contain color information. So for example, modeling different packet types, and also time information, modeling an age. And places and input arcs have time constraints for each of these colors. So in order to encode a network update into such a Petri net, we first need a gadget for injecting packets. So here in this gadget, initially a token is at this place on the left, and then we jump to the place S0 to generate a packet of arbitrary type. So different packets can be of different types, different timings, and we model this with different colors. Then we need a gadget for modeling the switch. So the switch can be in two states, either the packets go the old path or the packet go the new path. So this we can model either if the token is on the upper part or the token is on the lower part of the gadget. And then we also have different timing constraints for packets, so we can indicate this in the Petri net as well. Then we need a gadget to model the switch update, so how to change between initial and final switch configuration. And for this also we have a gadget that, starting from here, we model that the update can take between a certain amount of time, a lower bound and upper bound, and we can model this range of possible timings also in the Petri net. And then finally we need to connect the pieces, so we need to initialize the update sequence for multiple switches. So this we can do with this gadget that after updating switch S1, for example, we go to switch S2, etc. We can show that we can efficiently analyze these novel Petri nets by unfolding them into existing type of Petri nets, namely time arc Petri nets. And we can prove formally that this unfolding preserves bisimilarity. So it's a valid approach to evaluate and analyze and verify the Petri nets. Our approach comes with strong tool support. So Latte, our tool, translates the network update problem into this Petri net and then synthesizes minimal update delays. And we integrated this tool into the open source tool TAPL as well. And now you can also draw networks and you can also issue CTL queries to our model. And you can find online our tool on the TAPL website. Good. Some words about the performance of our approach. So we tried different network topology from network topologies from the topology zoo, and we see that up to a route length of 16, we can actually compute optimal update time. At some point, we will have timeouts because the amount of concurrency in this first set of experiments can be high. So this we could still tackle in future work, for example, with static analysis. We observed that compared to conservative delays as produced by the NetSynth tool, we can improve the latency by over 90%. We also considered a second scenario where, which is a little bit more complicated because updates cannot happen concurrently. So they require some minimal delays for the waypointing. And in this example, we see that actually the verification time improves. So we reduce the concurrency, and we can, like within seconds, we can also verify up to 70 switches. And the improvement is still over 90%. Good. Before I give you the demo, maybe just some pointers for further reading. We have a more broader perspective here on the verification in networks. And I would like to point you also to the Allwines website and our recent blog, and also the TACPN tool. Thank you.
Hello, my name is Niels, and beside me is Mark, and we are also the co-authors of this paper. And we will give a short demonstration of our tool inside TACPN. So first up, we will use the symphonous analysis where you can use this tool. So we will use the GML file, which is a standard topology of a network, and for this demo we will use the Oxford example. So when we're using the GML file, we have to define the routes ourselves, the pre and the post route, and we also have to define the waypoint that we have to visit. So when we press on start now, it will start calculating all the different updating sequences that are available. Some of them are true and some of them false. So as we can see here, now it has generated all this for us, and in the middle we have some predefined packages, package types as we're using in the paper, but you can define and change these as whatever you want. So we will take and choose to run the analysis. Now TACPN is running behind the scenes and creating the different components and calculating and optimizing the routes. So since we have update sequence of 3, we will have 2 consensus we need to update. As you can see over here in the right side, we have now started using bisection to calculate the different constances to the minimal values. And we can see down here in the bottom, the default time for the updating sequence was beforehand almost 8 seconds, which after we have optimized this, it was down to 0.5 seconds almost. And this is a percentage reduction of 94%. And if we close this now, here you can see all the different components that Stefan also mentioned in his presentation that TACPN has calculated for us behind the scenes. And if we go down to the update sequence, since we had 2 constances, we have these 2 different that are used down here that we can update the different routes with the maximum or minimal time limit. Over here in the right side, left side, we have the different constances that are calculated, and we also have the different packages types and the router's minimum and maximum updating time. So this is how we have done the results in the paper. Thank you very much for listening.